Okay, so you should have watched the video on the idea of a Monte Carlo calculation, or Monte Carlo simulation, or Monte Carlo integration, whatever you want to call it. And now we're going to take that and put it into code, and we're going to use the same function we used for the numerical integration, which is just we're going to integrate a parabola, y equals x squared, from the point x equals 0 to the point x equals 1. And we're going to calculate the area underneath that curve. So we're going to imagine that rectangle that goes from 0 to 1, and just putting random points in that rectangle, and then counting what fraction of those points to the total number of points fall underneath the curve. That fraction, as we add more and more points, will get closer and closer and closer to the area under that curve divided by the total area. And the total area in our example is just 1, right? A parabola goes from 0 to 1 in the x and the y axis. So the total area of our box is 1. That would change if we were using a different function. So I'm going to start by prompting my user. I'm going to ask the user how many points I'm going to generate in my simulation, how many darts am I going to throw at my square, and get that number and just put it into a double that I'm calling n. I know I say that you should use meaningful variable names for your variables when writing a program, but in this case, mathematicians use n to stand for the number of something all the time. So n is the total number of points, and I'm going to ask the user for that number. I'm going to stick it in a double. What variables am I going to need? Let's figure it out. I'm going to need the x and y coordinates for my point. So I'll create two doubles. I'll call them x and y. Those are just the coordinates of each point, x and y. I'm going to need for on my curve, I'm going to need to know what the y coordinate of the curve is. So if you think of in math class, we say like y equals f of x. I'll have a variable called f of x. And I can't put parentheses in a variable name, so I'll just call it f sub x. That's the point on the curve at that particular x coordinate. What else will I need? I need to count as I throw points in my interval, throw random points in my interval. I need to count how many are under the curve and how many are over the curve. I don't need to count the ones over. The number over is just the total minus the number under, right? So I just need to keep track of how many are under. So I'm going to create a variable called n under, which is just counting up as I go how many points have fallen under the curve. In fact, let's go ahead and initialize that at 0. And then I'm going to need the total area. I'll call that a subtotal. That's just the area of our interval from the maximum x to the maximum y. Since we're doing a parabola from 0 to 1, that area is just 1, right, from the point 0 to the point 1, 1. So our total area is just 1. I'll go ahead and make that a decimal. And I need a variable to hold the area underneath the curve, so I'll call that area under. And that we won't have to initialize yet. We'll calculate that as we go. So let's not initialize that at all. Just declare it. Okay, so we need a loop now. Our loop is going to put random points in this interval from 0 to 1. So let's do that. And it's going to do that starting from point 1 all the way up to n points, where n is the number that the user tells us to do. So we're going to have a loop that goes from 1 to n. So we've got 4. I'm going to cheat a little and look at my code over here on the side here because I haven't fully purged all the Python from my brain. The syntax is going to be n equals 1, semicolon, n is less than or equal to n, my total number of points, semicolon, n plus plus. So little n is just 1, 2, 3, 4, 5, 6, 7, 8, 9, up to a million, however many points I'm doing. N is just the number of point that I'm on. And big N is the total number of points. So the loop goes from 1 to big N. Okay? I need to start my loop with a curly brace. I need to end my loop with a curly brace. Okay? And then what do I need to do in my loop? I need to generate a random point between 0 and 1. So I need to generate a random x coordinate. And remember, when you're generating floating points or doubles, you can use the math.random method. And actually what that does by default is give you a number between 0 and 1. So I don't even have to scale that interval by. If I was doing a different interval, say from 1 to 10, I would take this and I would multiply it by 10, but I'm only going from 0 to 1. So math.random gives me a number from 0 to 1. I pick a random x coordinate and a random y coordinate. Did I? No, I don't have to. I was going to say, did I declare my my object from the random class? But I'm not using the random class. I'm just using the math class. Because all I'm doing is generating doubles, not ints. So I can do that with math.random. I don't need to import the random class at all. So that gives me a random point in my square. Now what question do I need to ask? I need to ask the question, is that point above the curve or below the curve? Well, to know that, I have to know where the curve is. Right? Where's the curve? The curve is y equals f of x. So let's calculate f of x. What is the value of the function at the x point I just generated? I call it f sub x. So what is f of x? It's equal to x squared, right? That's our function. Right? Our function is y equals x squared. So the value of my function at that point is just x times x. So I put a random point in the square. I ask myself, at that x, what is the value of the function? It's x squared. Now I ask myself, is the y I generated above x times x? If it is, the point is above the curve. Is it less than? If it is, the point is below the curve. So if y is less than f of x, okay, then what? Then I found a point under the curve. So I increment n under by 1. Okay, and this is going to need a semicolon. And I'm good, since there's only one statement being executed if this if is true, I'm just going to put it all in one line. Okay? So if the, I didn't need to type this, so. If the y coordinate of the random point is less than x squared, then we have found a point under the curve. Okay, if y of the random point is less than the function at that point, then we have found a point that's under the curve. If that doesn't make sense to you, go back and look at the pictures in the previous video and help kind of translate that, that diagram into code for yourself. I think that's it. That's our loop. For n equals 1 up to n, generate a bunch of random points. For each one, ask yourself, is the y bigger than or less than the value of the function at that point, which is just x squared? If it is under, then increment the n under by 1. So what we'll have when we're done with that loop is, of our n points, big N points, how many of them fell under the curve? That ratio is equal to the ratio of the areas. So I know that my area under is equal to the total area. Did I call it A under or area? No, I called it something different in my two programs. I called it A under. Let's call it area under, huh? Area under. My area under is equal to the area total times the ratio of points under to the total number of points I threw at my square, right? So n under divided by n, semicolon. Let me say that again. The area under my curve is equal to the total area of my square, my rectangle, my interval, times the ratio of the number of points that fell under the curve, the number of random points that fell under the curve, to the total number of points I threw at the square. And then I should just be able to print that out. I'm going to copy and paste this so you don't have to watch me copy and type out a whole print statement. So I've got system.out.print. The computed area under the curve is, and then area under my variable that I just calculated. Okay. So I think that's it. If there's no mistakes, if there's no compile time errors, we should just be able to run this. There you go. So how many points? Let's start with something small. Let's start with 10. The computed area under the curve is 0.5. What should the area under the curve be? Remember, it should be a third, right? What are we integrating? We're integrating the function y equals x squared from 0 to 1. That's a third. Again, if you don't know the calculus in the past couple of videos, we've just talked about the fact that we know mathematically that the area under that parabola is equal to 1/3. Well, 0.5 is not particularly close to a third, but 10 is not many points to throw at this. Just like when we divided the interval into 10 rectangles last time, we didn't get a very close answer either. So let's do more. Let's run it again. Let's throw 100 points at the interval. 100 random points. I get the computed area under the curve is 0.36. Let's do more. Let's do 1,000. We throw 1,000 points at the interval, we get 0.326. Let me make this smaller. Okay. Let's do, oops. I started typing before it got done asking me. How many points should I generate? Let's do 100,000. 1, 2, 1, 2, 3. Ah, now we're getting somewhere. 0.3344. So now we're down to about 1%. Let's keep going. Let's do 1,000,000. 1, 2, 3, 4, 5, 6 zeros. 0.333417. Let's do 100 million. Will it let us get away with 100 million? 1, 2, 3, 4, 5, 6, 7, 8 zeros. 2 blinks, 3 blinks, 4 blinks, 5 blinks. Okay, it took longer. It took about 5 seconds. Notice this is not converging on the answer as quickly, right? In the last program where we're doing numerical integration, when I did 100 million points, I was getting out to like 6 or 7 decimal places. Here I'm only getting, with 100,000 points, I'm only getting out to 3 decimal places, maybe 4 decimal places. So the speed at which this converges on the answer is slower. But the amount of computation I am doing is much less. In the last program, I had to compute the areas of all those rectangles and add them up, which means I had to find the value of the function every time I did that. So the other method is a little more computationally intensive. And imagine if the function was more complicated than just y equals x squared. Imagine if it was the 50-page function I had in my PhD thesis. That would make it much more computationally intensive than just throwing random numbers in the square and seeing if they're higher or lower. I doubt that CodeHS will let us get another decimal point. I just did 8 zeros. 9 would be a billion. I don't think it'll let me get away with a billion. Let me try. 1, 2, 3, 4, 5, 6, 7, 8, 9. A billion points? Probably not. We'll try it. And I'll talk over it while I try it. So Monte Carlo simulations are not as fast converging on the answer as numerical integration methods in general, but they are more straightforward to calculate. So it's blinked maybe 10 times now. It's still working. I don't think CodeHS usually doesn't let us go up to billions in our loops, so it'll probably time out on us. That's okay. It's good to know the limitations of these things. In fact, a good homework problem would be for me to give you a Monte Carlo calculation of some known function or some known value. You can use a Monte Carlo simulation to calculate pi, for example, and ask you how many points does it take you to get to 3 digits of pi? How many points does it take you to get to 10 digits of pi? Can you get any better than that with a Monte Carlo simulation, or are we limited? Oh, we timed out, so we can't do 1,000,000,000 points. 100,000,000 is our limit. Okay, so this is another tool in the toolbox of mathematicians and people who use computer program to do mathematical things. Another technique for calculating things that are too complicated to calculate by hand. And Monte Carlo calculations are used a lot by physicists, by engineers, and it's good to know what they are. Even if you never use them for anything in the next couple of years while you learn how to write programs, it's good to know that the technique exists and have experience with these things like numerical integration, because they make up a big part of what scientists are up to when they're using or when they're writing code to do calculations. So I just thought I would give those 2 examples this week of some mathematical applications of some of the programming tools that we've learned so far. Yeah, and I think I'll leave it at that for now.